All right, we ready to go? Yes, yes, good answer. Today we're going to continue talking about failure criterion. And what we do today is actually going to be very similar to the thing that we did when we met last time. We are still talking about another theory that bears the name of Coulomb Mohr. But what we're doing today is we're applying it to a different type of material. So what we did last time is actually called Ductile Coulomb Mohr, and it applies for materials that are ductile. So if you think about the stress-strain curve, that would be strain down there, stress up here. What you have for the stress-strain curve, if it's a ductile material, it has a linear portion generally, and then it has another portion where it goes more horizontally and curves. So the first portion that's linear, that's called the elastic region, and then it goes into the plastic region where it has the curved part up there on the top, and then eventually it breaks. All right? And what we have done with our failure criterion so far, we have been looking at how to determine when something will fail based on the idea that right there at the point where it stops being elastic, we count that as a failure. All right? So what we're doing today is a little bit different because we are going to apply it to materials that are brittle. And brittle materials don't have a curve that's shaped like this one. All right? Most of the time, a brittle material is going to have a curve where it actually isn't very curvy. It might go up along a relatively straight line, and if it's a really, really brittle material, then basically it goes up and at some point it breaks. All right, and there's not much of a plastic range for the material. Pretty much, once it reaches that highest stress level, and what's going on in there is that the little bonds, some materials have the ability for the little bonds that are inside of the material to sort of rebond as it begins to deform. And some materials don't have that ability. And so what you have with a brittle material is that as soon as you have some of those bonds that break, well, then there's that much less area that's helping to share the load, and you go to a really fast failure of the entire cross-section that's carrying the load. So what we're doing here is we're going to look at some theories that handle this type of material. So the other thing that I'll say about this is that a lot of these brittle materials do exhibit asymmetric strength properties. So we looked at that last time. That's what we did with our Ductile Coulomb Mohr. We looked at some ductile materials that might have different properties in tension relative to compression. There's actually not that many of those. Most ductile materials exhibit relatively similar strength properties in tension and compression. All right? Whereas once we go to these brittle materials, it becomes much more common to have different properties in tension versus compression. And one of the things that we'll see in today's example that we do toward the end is that the amount different that they are can actually be quite a bit bigger. The amount of difference between the properties in tension and compression can actually be very significant. So that's going to be interesting today. And what you'll see here is that because this curve doesn't really have the curved part of it that moves over to the side, because it's not there, what we did for our Ductile Coulomb Mohr theory can basically be brought straight over here to this theory and used in exactly the same way. So I'm not really going to rederive it. What I will do is I will show you this figure that I have. You'll see this figure that's toward the right over there. All of those little points that you see on those squares, those points represent data for materials that were loaded to various states of stress. So the fact that they're in different locations along that perimeter of that shape, that means that they were loaded such that they had different relative amounts of principal stress, and we're plotting where does it end up failing. All right? And what you see here is that the theory we derived when we were here last time is represented by this line that goes right there. And you look at that line, you say, does that line do a very good job of representing those data points? And I would say not really, okay? It is safe in that it is inside the data points, right? We've talked about the idea of being conservative. And the fact that that red curve that I just drew on there stays inside of where the data points are located, you know, it kind of makes us feel good that we're probably not going to experience a failure with our material at lower stress levels than we predict a failure if we use that red line. But it might mean that we are we might be over-designing parts if we are using that as our curve. And so there's another option that we can go with. By the way, the red curve right there, that one is called the Brittle Coulomb Mohr criteria. The other one that we have over here is called the Modified Mohr criteria. And the general shape of that criteria is still two straight lines in that region, right? In the fourth quadrant down there, it is still two straight lines. But now what we do is we allow the vertical line that existed above the horizontal axis there, we allow that to extend down all the way to the point where we hit a state of pure torsion. That's what this line right here is. Okay? Pure torsion is where you basically have one of your principal stresses equal to the negative of the other principal stress. That's what you have at the state of pure torsion. And this failure criteria allows that curve to extend still vertically down to where it hits that torsion line and then cut over to the state of a pure uniaxial compression. All right? And I'm not going to write them all down, but on page 250 in your book, I guess I'll write that down, page 250, we have the equations for both of these criteria. So for Brittle Coulomb Mohr and Modified Mohr. Okay, and I'll look back at those whenever we get ready to start working an example. All right, so this is the basic idea. The next thing I want to kind of go through, because this is our last failure criteria that I will introduce. These are the last couple of them. Actually, I missed one thing here. The other dotted line that you see here is labeled maximum normal. The book kind of talks about that criteria a little bit. No one ever uses it. It is not conservative. It doesn't do a good job of representing when materials actually fail. It's kind of in here as a historical note that people may have taken it seriously at one point in time, but no one ever uses it anymore. So I'm not really going to spend much more time on it. So yeah, basically the shape that you have for a maximum normal criterion is this outside square. And you see here, that is especially bad if you have a fairly compressive force and a smaller tension force, or excuse me, compressive stress and a smaller tension stress. You know, down in this range down here, if you had a load line, for instance, that was going like that, right, you wouldn't predict failure until it reached that line. And that's not good because the data says that your material would fail significantly before that, most likely, if it followed the pattern of the rest of this data that we have up here. So that's, you know, I mention it here, but we're not really going to do anything with it. So suffice to say. All right, let me do one thing here. How do you know which failure criteria you should use? All right, so here's kind of your breakdown on what you do. You first ask the question, is it brittle or ductile? Okay. Is it brittle or ductile? All right, how do you know if it's brittle or ductile? Okay, the book uses this, you know, the variable that they use for this is epsilon f. That means our fracture strain, okay, and that's essentially how much strain it can take before it fractures, not surprisingly. If this is greater than or equal to 5%, then we are ductile. Okay? If not, then we are brittle. Well, then what? We have two choices that we can do over here. We have in one case, we have a theory that better represents the data, right? And we have a theory that's more conservative. Okay? So kind of have to think about what is it you're trying to achieve with your theory. All right? So at this point, maybe I'll make a big thing like this and say, if you want more conservative, we go over here and we choose which one? Okay, right now we're on our brittle side, right? So we are doing, okay, remember BCM, if you go back up here, your Brittle Coulomb Mohr is the red curve. The red curve is more conservative, right? It's also a little bit simpler as far as the mathematical construction of it. Okay, over here, matches data better, typically. All right, in that case, we go down and we do which one? Modified Mohr. Okay, over on the ductile side, the first question we got to ask is, do we have symmetric strength properties? Okay. Same yield strength. In tension and compression. Oh, that's a decision also, right? Same yield strength and tension and compression. Okay. What if yes? Okay. Then we end up with two options. How do we choose? Okay. It's the same as over here. Do we want one that's more conservative, or do we want one that matches the data better? Okay, if we want more conservative, what do we do? Okay, this one over here is your maximum shear stress theory, or Tresca. And over here, what do we have? Distortion energy. Okay, what if we do not have the same strength properties over here? Okay, yeah, DCM. Right? Ductile Coulomb Mohr. Because remember, we're over on the ductile side of all the question. Okay? And so if you're trying to decide on one of these criteria, this is one way that you can figure through that and figure out which one you might be most interested in. Okay? Quick encouragement on this particular point. There are some times where I do want you to look through some data tables, and many of the data tables where it gives material properties, it will give you this information of whether you have a ductile material or a brittle material. Okay? Don't ignore that information. All right. Questions before we go into our example problem? All right, here it is. What we have here is a cylindrical tank that is set up vertically. The cylindrical tank is carrying a fluid that is held at an internal pressure of 100 psi. The wall thickness of this vessel is 0.175 inches. All right, it is carrying an additional 100 kip force on the outer perimeter of the tank, and that 100 kip force is directed along that dotted line, and the trajectory of that force is given with the dimensions that I'm showing there. Okay, see how that works? So basically, if you extend the line of action of the 100 kip force down to the XY plane, it will intersect at 60 inches along the Y and 30 inches along the X. Okay? And what we're going to try to do here is we are going to try to figure out what the factor of safety is for patch 1. And we're going to use both of our brittle failure criteria. Okay? We're going to do it with Modified Mohr as well as for Brittle Coulomb Mohr. All right? So that's what we're going to do. In the interest of time, and because we've done this particular part of the problem quite a bit at this point, I am not going to spend a bunch of time coming up with the magnitude of the reactions at the base of this tank. Okay? So what we have here is that we will have a reaction in the X direction as defined on my figure there. Notice the direction I've put those forces. I chose them that way on purpose so that the directions would be fairly clear just by looking at the figure rather than having to deal with doing swaps because of sign differences and everything. So they all turn out positive is basically what I'm saying. I chose the direction such that that would happen. Okay? You also see the Y direction and the Z direction. And these are the reaction forces that happen at the base. All right? One quick other comment that I will make that I don't think I mentioned yet. We are going to assume that where this tank is being supported at the base, we are going to assume that the base is not supporting any of the hoop stress. We're going to assume that the tank is internally supporting hoop stress that might happen due to the internal pressure. Well, really the hoop stress and the axial stress due to the internal pressure. We're assuming that the structure of the tank itself manages those things. All right, so there's my force reactions that I have at the base of this tank. And here are my moment reactions, which might be worth talking through a little bit more. Okay, particularly my Y moment. All right, you notice there I have two different components that happen for my Y moment. Why is that? Okay, we split that 100 kip force into a couple of different, three different components. And one of the things that you will see is that the moment that is created about the y-axis is influenced by both the z component of the 100 kip force as well as the x component of the 100 kip force. So for both of those components of force, there is going to be a reaction that has to happen moment-wise around the y-axis. Is that true for any of my other axes? Okay, let's think about the x-axis. Only the y component of the 100 kip force is going to create a moment around the x-axis. Right? That's the only one, because the only other one that could potentially create a moment around the x-axis would be the z component, and the line of action for the z component passes that we would be summing about, so it's not going to contribute. Okay, let's take a moment and look at the z direction, or around the z-axis. For that one, your two components of force that could create moments would be the x and y. Okay, and of those, the x component that you have of the 100 kip force has a line of action that passes through the z-axis, so it will not create a moment, whereas the y component its line of action does not pass through that axis, so it would create a moment. All right? And so there are the three components of moment that happen at the base. All right? Questions so far? Yes, sir.
Will it matter later on or the fact that you drew them so that they were all going to be positive instead of the normal convention of the right hand rule?
It won't really, it's going to make it more clear easier, right? It's going to become more clear, and it will be an easier process of making it clear by having them drawn how I have them, because we won't have to do any sort of mental gymnastics of thinking about, I have the force drawn in one direction, but the value turned out negative, so I really have to reverse it. Instead, it should all be more clear on its face. Yes, sir. Okay. All right. The next thing I'll do here, just while we're on this topic, let's go ahead and look up the material properties for ASTM 30 cast iron. All right. We do have a table for this in the back of Shigley. ASTM 30 has a tensile strength of 31 KSI and a compressive strength of 109 KSI. Okay, this is from table A24. Okay, we're doing ultimate strengths now. So we have an ultimate strength in tension that is 31 KSI and an ultimate strength in compression of 109 KSI. Okay. So we've taken care of the idea of where do we go to find our strengths for our material. All right, now what? We need to find some stresses. And boy, do we need to find some stresses, right? We have several of them to find. All right? So I'll tell you what I'll do. The patch that we're trying to look at here, patch 1, and you'll notice I have another patch on there. I don't know if we'll have time at the end. If we have enough time, I might do another patch, but if not, then I'll let you do that on your own. All right? So for patch 1, let me do this. Let me draw it somewhat larger. Okay, so I'll draw it over here. Okay, and as we come up with our components of stress that are going to be applied to this patch, I will try to draw them all on that patch of material separately so that we keep track of which one we are dealing with at each time, and then we'll add them all together at the end. Okay, so this is patch 1. All right, which components of stress would you like to start with? Okay, axial stress in the Z. That one's easy, right? So I'll do down here axial stress. And I'll say due to FZ. Right? So what's my axial stress due to FZ going to be? Well, FZ is 85.44 kips. Okay, and so the stress in the Z, and I'll actually just call this axial, like this, is going to be 85.44 kips divided by what? The area. The area is going to be pi over, well, I'll tell you what, we are actually given radius values, right? We have a 20-inch outer radius. So rather than use the formulation of it with diameter, I'll just use the one with radius, pi r squared. So pi times 20 inches squared, but then what else do I have to do? Okay. Yeah, I have a wall thickness that is given of 0.175 inch. Right, so I have to take 20 inches minus 0.175 inch. Okay, and I believe I have that worked out in here, so I don't have to spend too much time with it. See if I can find it. All right, we have 3,902.27 psi. Okay, and actually we need to think carefully about this. Is that positive or negative? Okay, Fz was positive, but if Fz is positive, it creates a compressive stress in this structure, correct? So I need to make sure that I'm consistent with that. Really, this would have to then be negative, and the outcome here would be negative, indicating compressive stress. Okay? So I tell you what, I'm actually going to show this on here as a compressive arrow. Okay, and I'll start over here. And I don't mean, when I sort of am spacing these out on the patch, I don't mean that there's parts of them that are applied to one part of the patch or whatever. What I mean is that I'm going to show several of these different stresses that will all combine together using superposition. And so we'll be able to sort of independently label them. All right. So here, stress, the axial stress, is going to be 3.9 KSI. All right, good deal. What next? Okay, maybe we should handle bending. Okay, I don't disagree with that idea. So, normal stress due to bending. Okay, for that we are going to use MC over I. Okay, and which M do I need to deal with to figure out my normal stress in that patch due to bending? My. Okay, that's correct, My. So the fact that I have a moment around the y-axis and, you know, given the direction of that moment, it's going to tend to create a compressive stress in that patch 1. Okay, so I need to figure out what the value is of that stress. My is 2562.8 kip inches. So my stress then is going to be equal to 2562.8 kip inches. What is C? Okay, because I'm given radius at the very beginning, that is the distance from the neutral axis to the outer fibers of this beam, right? So I'm going to use 20 inches here. What about I? Okay, pi over 64. Yeah, we could use the formulation with R. Since I started with this, I'll go ahead and finish with this. We would use our diameters if we use the pi over 64. Okay, and then for our other term here, we would have 40 inches then with what? Minus, okay, we would need 2 times the wall thickness, right? So 2 times 0.175 inches. And then that would all be to the 4th. Okay. And what I have for that is 11,807.9 psi. Okay. As the magnitude. Now let's think about the direction. Right? We already mentioned it, but what direction does it apply? Okay, look at the direction of the moment. If my is applied in the around the y-axis in the direction shown, that is going to tend to lead to a compressive stress in patch 1. Okay, so what I'm going to do, I will show it as a compressive stress on here. All right, tell you what, I'll write this one down here. 11.8 KSI compressive stress. And this is due to flexure.
You said it's compressive? Yeah.
It is compressive. Okay, do we need to look at that a little bit more? Okay. If I try to take the bottom of this tank and rotate it the direction of my, and the tank stops me.
Okay, so the moment's at the bottom and it's making it. Okay.
Yep. It's going to tend to try to compress patch 1, and if there was one opposite on the other side, it would try to elongate it, put it in tension. Okay, so it is a compressive stress on the patch 1. All right. What next? You want to do your, okay, we can do that if you want. We can do our pressure vessel stresses. What I will do here is flip over to that portion of the book where it talks about the stresses that you have due to pressure vessels. Okay, well that's a good question. What guidance do they give in the book about whether you should use thin wall or thick wall? Okay, so let's look real quick. I believe it says in here, let's see here. When the wall thickness of a cylindrical pressure vessel is about 1/10 or less of its radius, the radial stress that results from pressurizing the vessel is quite small compared with the tangential stress. Okay, and basically what this kind of means is that you can sort of pretend like the stress is relatively uniform across the cross section. All right, so what do we have? All right, we definitely make it. It's not even close. Right, definitely a thin-walled vessel. All right, so we need to evaluate 2 things. We need to evaluate the longitudinal stress and the hoop stress. Okay, let me start with the longitudinal stress. It says that you use the internal pressure times the internal diameter divided by 4 times the thickness. Okay, so this is for pressure vessel stresses. Okay, what they call longitudinal. It's going to be the internal pressure of 100 psi. Okay, what's the internal diameter? Okay. I'll say the internal diameter is going to be 2 times the internal radius, and the internal radius is going to be 20 inches minus 0.175 inches. Okay. Then what do we have in the denominator? 4 times the wall thickness. Okay. And what I have calculated for that is 5,664.3 psi. All right, for the next one, there's a formula given up here. It says we need the internal pressure times the internal diameter plus thickness, all over 2T. And that gives me my hoop stress. Okay, so it'll be 100 psi. By the way, let me make a note up here. This is on page 128. These are equations 353 and 354. Uh, 353 and 354 are the equations, page 128. All right, 100 psi times internal diameter plus thickness. Okay. What's actually true there is that if you're going to take the internal diameter and add thickness, what if you have the outside diameter? You could subtract thickness, right? What you're doing basically is going to the center line of the wall of the pressure vessel, right? So I'm going to actually write it that way, where I do the outside diameter minus the thickness. All right, and then the denominator, I have 2 times the wall thickness. Okay, and this gives me 11,378.6. PSI. All right. So what do I need to put on my patch? Yeah, the longitudinal piece, I'm going to use a different color. Is it in tension or compression? Tension. Because it's basically, imagine if you had end caps, which you do on this pipe, that internal pressure pulls on those end caps and it creates a stretching action on the pipe. It tries to make it longer, and the material is what holds it in. That means that you are going to have a tensile stress on those patches of material. Okay? That's for longitudinal. And this is going to be equal to 5.6, we'll just say 5.66 KSI. All right, what about my hoop stress? Okay, yeah, it's going to go in the other direction, right? It's going to go in this direction. And its value here, that's my hoop stress, its value is going to be 11.38 KSI. All right, so now we've done our pressure vessel stresses. Okay, what else do we have to do? We have a couple of different sources of shearing stress potentially here. All right, let's do the easy one first. What's the easy one? Okay, probably the one due to torsion that happens on this tank. So we'll say shearing stress due to torsion. Okay, why don't we figure out the magnitude first? Let's figure out what the magnitude of the torsion is going to be. Which of my reaction components is the reaction component responsible for the torsion? Okay, it's the one around the Z. And as I'm looking at my little drawing here, I actually kind of want to move this down here. Why is that? I mean, it gets really messy if I do that, but I think that actually does a better job of describing what that reaction means. Okay? It means that it is applied at the very base of this tank, right? Which means that the direction that that moment is acting is really, you can imagine it acting on the bottom side of the patch of material that we are looking at. All right? So this is important for us to get these right because we're going to have to combine this with another component of shear because we're going to have to deal with the transverse shear due to the, it'll be due to my Fy force component. All right, so it's acting there on the bottom. What direction does that cause stress on that patch? I'll go ahead and draw it on here. Okay, the moment, I'll do this in a different color here. The moment creates a shear like this on the patch. Okay, and so this is my tau due to torsion. And my tau due to torsion is going to be based on the formula Tc over J. All right. The torque is, as we said a second ago, mz, and mz is 1025.22 kip inches. Okay, what is C? Right, still 20 inches, that's the radius, outer radius of the tank. And what do I put in the denominator? Okay, we can go ahead and do it in terms of diameter. We get really used to doing it in terms of diameter, so rather than risk using the wrong formula, we'll just go ahead and do it again that way. What is the diameter of the tank? Okay, the outer diameter is 40 inches. And the inner diameter is 40 inches minus 2 times 0.175 inches. All right, so what we need to do now is figure out what that value is. I believe I have this one written down as well. Just need to find it. 2,361.8 psi. Tell you what, I'm doing all these in terms of KSI. That is going to be 2.36 KSI. All right, we're getting close. You feel it? You can feel it? All right. So now, we saved the best for last, right? Transverse shear.
Easiest to visualize.
Easiest to visualize? Okay. It really isn't bad. So the way you can think about this is look at the direction of Fy. Okay? And think about Fy being applied to the bottom side of the patch. All right, that's where the tank is being supported, is on the bottom side. So think of the direction of Fy being applied to the bottom side of the patch. Okay, and so the direction for that force is going to be the same as for the direction of the moment, or the torque. So I'll write that on here. I very quickly run out of space, but I'll put it on here like this. Okay, so now we have to figure out what the value is on that. The formula that we use for transverse shear is VQ over IT. Okay, and let's go and remember our, we have a pretty slick deal that we can do for Q if we have circular cross-section. Does anyone remember what that formula was? Okay, yeah, outer diameter cubed over 12 is that first moment of area that we calculate with Q. Okay, so let's start putting these in here. Our transverse shear is going to be equal to Fy, okay, which is 51.26 kips. Calculating Q now, we take the outer diameter, cubed. But then what? It's not solid, right? This cross-section's not solid. So what do I have to do after that? Subtract the inner diameter cubed divide all that by 12. And then in the denominator, I need the I value, pi over 64, times 40 inches to the fourth minus 40 inches minus 2 times 0.175 inches, all of that to the fourth. Okay, so there's my I value that we actually have previously computed, but I didn't have it separately, so I wrote it all out again. All right, last parameter here. What else do we need? T, right? We need to know how much thickness did we have at the cut. So what you're imagining doing there is we made a cut essentially along this axis right here. And we cut through a little bit of material when we cut right there, and we cut through a little bit more on the other side of the tank. Right? Each time we cut through the material, it was a thickness of 0.175 inches. And so we need to put in here 2 times 0.175 inches. All right, so let me see what I've got for that value. There it is. 4,682.3. PSI. All right. Have we accounted for all of our stresses on this patch? I think so. Yeah. Let me go ahead and define my directions on here. We had, we're running out of space here, but what direction was up? Z. And what direction was this way? Okay, that was Y. Okay, so out of here, what is my Z component of stress? Okay, it's going to be equal to 3.9 KSI compressive stress, 11.8 KSI from flexure, and that's also compressive. And then I have a tensile stress because of the internal pressure, and that tensile stress is 5.66 KSI. Okay. And so that ends up totaling up to a negative 10 point, I'll keep just 2 decimal places here, 10.05 KSI. All right, what about my Y direction? And that one doesn't need any extra processing because we just have the one component from hoop stress that goes in that direction. Okay. What about my shearing stress in the YZ direction? Okay. 4.68 KSI plus 2.36 KSI. And that ends up being, I have 7,044.1 PSI, which is 7.04 KSI. And for the question we're trying to answer, the direction of the shear doesn't necessarily matter as far as the actual sign convention of the shear. It doesn't really matter very much for this question that we're trying to answer. That is the factors of safety question, right? We don't necessarily care what direction the principal stresses are oriented on that patch, right? But it is actually stated correctly on here. All of these signs are stated correctly anyway. All right, so there are my components of stress. Now what do I do? Yeah, now we need to find some principal stresses, because that's what we need when we deal with our failure criteria in general. Okay, so how do I find my principal stresses? Okay, we could do stress invariance, all right, but this is a state of plane stress. Okay, so we don't necessarily need to go to all the trouble of stating it all in a, you know, a tensor and then doing all that math of figuring out. We can just use Mohr's circle calculations. Okay, and here are Mohr's circle calculations. Okay, my first in-plane principal stress, what I need to do is take the average of my normal stresses for the first term, right? So I take 11.38 KSI, and I add a negative 10.05 KSI over 2. So that's the first term, and when we're doing our Mohr circle calculation, the first term is the average of the two normal components of stress. Okay. To this, I have to add the radius of Mohr's circle for my in-plane stresses. Okay, and the radius of that is going to be the square root of two terms, one of which is the difference in my normal stresses over 2. Okay, my normal stresses again are 11.38 KSI minus a minus 10.05 KSI. Okay, all of this over 2 and squared. Okay, and then the next term in under the radical down there is I need to take my shear. And square it. All right. And before I do the answers to this question of what my principal stresses are, my second principal stress, in-plane principal stress, is almost exactly like this one as far as how it is stated. Okay, so my B, what's the only thing that changes? Okay, and what I get for my in-plane sigma A is 13.49 KSI. And for sigma B, I've got negative 12.15 KSI. All right, so there's my, my in-plane principal stresses. Now I need to do factors of safety. Good news is this part's pretty easy, right? The worst is over now. So I'm going to go back and we'll first do Brittle Coulomb Mohr. Okay. So first we need to figure out, where are we at in terms of our principal stresses that we've got. Do we have opposite signs? Okay. That means that we are on equation 531b. Okay. And actually it's stated in terms of 1 over this. And I'll put it over here. This is equation 531b. And it will be sigma A, which is 13.49 KSI, over my ultimate strength in tension. And we wrote that up here at the very beginning, 31 KSI. Minus a minus 12.15 KSI over my ultimate strength in compression, which was over here, 109 KSI. And the factor of safety that I get when I calculate that is 1.8295. I'll just say 1.83. All right, the next one we want to do is Modified Mohr. Okay, this one might be a little more thinking for us to figure out which of our equations we would like to use. If I take the ratio of sigma B over sigma A, okay, in other words, I put the one that's negative and put it over the one that's positive. Do I have a ratio greater than 1 or less than 1? Okay. Since I have a ratio less than 1, where that puts me on my failure locus that I had way up here at the beginning, if I have a ratio of less than 1, it means that my load line is going to lie somewhere up here above that break, which means I'm still on this vertical line. Okay? And because of that, we would be using equation 532a. One over that, actually let me see here. It's stated differently, I believe. We can just do it this way. N of modified Mohr is going to be equal to S sub ut over sigma A. Okay, the reason why is that if you go back up and look at this plot, since our slope is less than 1, if I take my sigma B over sigma A, that slope is less than 1, it means I'm in this vertical portion of the line, which means that my sigma A component is the only one that matters with respect to where does it cross. Okay? So that's why the equation that we're using does not include, got to find it, there we go, does not include sigma B. All right, so sigma A is 13.49 KSI. And so my factor of safety that I have for modified Mohr ends up being 2.29. Okay. This problem illustrates, one of your worst case scenarios in terms of the difference between BCM and Modified Mohr, Brittle Coulomb Mohr and Modified Mohr. It's one of your biggest differences that you'll have for any states of stress. Okay. What I'm going to do, oh, yes, sir.
The only major difference between Brittle Coulomb Mohr and Ductile Coulomb Mohr that you use ultimate strengths for brittle?
That's right. And for brittle materials, very often they will not publish any sort of a yielding strength for brittle materials because it a lot of times doesn't make sense for brittle materials to try to publish that data. So there really isn't a difference, no. All right. We're approaching the end of our time together. What I'm going to do, because I'd like to get this done, is I'm going to go ahead and plot the failure locus. You're welcome to stay if you'd like. You do not have to stay if you don't. But if you want to leave, please try not to make too much noise on the way out. So, all right, the failure locus. Okay. The failure locus is fairly asymmetric. All right, I'm going to make these squares worth about 10 KSI each. So I have 31 KSI and 31 KSI. Okay, and then I have down here roughly negative 109 KSI. And negative 109 KSI. Okay, and then I need to plot the load line, which I will plot with a positive 13.5 or so KSI to the right, which will be, we'll say somewhere in here, and then I have negative 12.15. So there's my load line. And relative to the Brittle Coulomb Mohr criteria that I have drawn on here, does it make sense that I'm about 1.83 or 1 over 1.83 amount of the way to the failure criteria? It looks like that's a pretty good estimate to me. In other words, 1 over 1.83 would give me the percentage of the way I am from 0 out to that failure locus.
That yellow line is what now?
This is my load line. Okay. All right, let me actually plot my Modified Mohr line as well. So Modified Mohr would come down like this to about here, and then down like this to there. And you can see that that creates a little bit further that you would have to go with that load line in order to get out to the failure locus. Okay, so the red is BCM, the dotted line there is my Modified Mohr. And they look like they are consistent with the factors of safety that I calculated. Yes, sir?
How far for the Modified Mohr, how far down you have to go? And then, like, you go
Okay.
down on the Y direction.
Yes, so there's a couple ways you can see that. The way you can think about it is it breaks right at a state of pure torsion. Pure torsion happens when your two in-plane principal stresses have opposite sign, same value, opposite sign. Okay? And so that basically is the slope of -1 is what you kind of think of there.
So, all right.
Other questions? All right. Well, thank you for your attention. Hope this was valuable, and I will see you next week.